Hello, everybody. If you're in the 8 o'clock class, you know I'm laughing. If you're in the 9 o'clock class, don't worry about it. But who's all here? Say hello. Good morning, Emma. Good to see you. William, good morning. Good morning, Maddie. So you are all from the 9 o'clock class, so you don't know the confusion. I'll explain it in a second. Mia, good morning. Okay, well, Liza, Navik, good morning. I guess we could join in on the simultaneous sip, and then I could explain why I was laughing. So if anybody wants to join, just type the word sip in the chat. So I'm laughing because I just gave the 8 o'clock class their quiz because I know they don't have class besides my class at 8 o'clock. But I gave them a calculus quiz. So I think it's fixed at this point, but I'm going to be checking my email throughout the stream to just make sure everybody's gotten the linear algebra quiz at this point. Okay, and so at around 9:40, I'm going to end the stream today, so you guys all have plenty of time for your quiz. Okay, so we're going to continue working on section 5.2. We ended yesterday by talking about the characteristic equation. We're now going to define the characteristic polynomial. It's the same thing as the characteristic equation, except we won't have the equals 0 part at the end. So if A is an n by n matrix, then the determinant of A minus lambda I good morning, Cruz and Echo. Then the determinant of A minus lambda I is a polynomial of degree n and is called the characteristic polynomial. Of the matrix A. Okay. So it's just some more terminology. So instead of saying characteristic equation, which is when we took our determinant of A minus lambda I and set it equal to 0, this is just saying what's the left-hand part of that equation. That's the characteristic polynomial. So, for example, so let's say the characteristic polynomial of a 6 by 6 matrix is lambda to the 6th minus 4 lambda to the 5th minus 12 lambda to the 4th. And the question is, find the eigenvalues and their multiplicity. Okay, so I'll give you a few minutes or about a minute to think about this, but does somebody want to say in the chat if they have an idea of how they're going to find the eigenvalues from the characteristic polynomial? Okay, maybe we're not sure. Remember, to get the eigenvalues, we set the determinant of a minus lambda I equal to 0. So we would set our characteristic polynomial equal to 0 and try to solve. Yeah, exactly what Taylor said. So we'll solve for lambda, and the way we'll do that is by factoring, and then the power of each of the factors is their multiplicity. So lambda to the 6th minus 4 lambda to the 5th minus 12 lambda to the 4th is equal to, well, we could factor out a lambda to the 4th. And we get a quadratic. So lambda to the 4th times some quadratic, and we can factor this just by factoring or completing the square, whatever your favorite technique is. Quadratic formula. And to find the eigenvalues, we set it equal to 0. And so our eigenvalues are 0 with multiplicity 4. Six with multiplicity 1. And negative 2 also with multiplicity 1. Okay, so from the characteristic polynomial, we could find the eigenvalues and their multiplicity. All we do is just factor, and it tells us all we need to know about the eigenvalues and their multiplicity. So if you have any questions, just type them in the chat. I'm going to start writing out the next example. So we'll let A be the 2 by 2 matrix, 5, 3, 3, 5. And what we want to do is find the characteristic polynomial and then find the eigenvalues. Okay, so yeah, I'll give you, let's say, a minute to work this out. As a reminder to those of you in the 8 o'clock class, well, one, I'm sorry for posting the wrong quiz at first. But if you haven't looked at the quiz yet, you have 21 minutes. So I would I would stop this live stream, go over to Canvas, quickly fill out the quiz, and come back. Those of you in the 9 o'clock class, you have nothing to worry about. And if you're working out this example, could you somehow communicate to me that you're finished or that you're not sure where to go by just writing something in the chat? You could either do like some words, or you could put in funny emojis. Really, whatever you want to do. Keep me entertained. It's a little boring here, just talking to a laptop over and over again. Yeah, good, Taylor. So you got 2 and 8, and so I think we could probably talk about it now. We want to find, Sam agrees, good. We want to find the determinant of a minus lambda I. We'll set it equal to 0 and then solve. Okay, am I out of touch? I've never seen the double, the arrow, the little caret things here. And both Sam and Noah have done those as, maybe I'll start texting with those. Okay, sorry. We want to, let's find the determinant of a minus lambda I. So let's try to get out of my spotlight there. A minus lambda I is the matrix. Well, the first entry will be 5 minus lambda. 3 will stay the same. 3 will stay the same, and a 5 minus lambda here. Oh, got it, Noah. So let's find the determinant of this matrix, and a determinant of a 2 by 2 is nice and easy. You just do the cross multiplying. So this is the characteristic polynomial. So it's 5 minus lambda squared minus 9, which works out to be lambda squared minus 10 lambda plus 16. So if you factor this out, combine like terms, it should reduce to this. Okay, and how do we get the eigenvalues from the characteristic polynomial? This delay is going to be too long, so I'll just pretend somebody answered. Yes, you set it equal to 0. Okay, perfect. So So to get the eigenvalues, we'll take our characteristic polynomial, set it equal to 0, and solve. And 16 factors to 8 times 2, which adds up, or negative 8 times negative 2, which adds up to negative 10. Okay, so here we got, we found both of our eigenvalues, and we weren't given a triangular matrix to start, but we were still able to find the eigenvalues using this determinant method. So let's look at one more example like this before we move on to 5.3. So we'll do the same example. So repeat previous example. With this 3x3 matrix. And now I will advise you, let's try to be smart with how we compute the determinant of this matrix. Okay, so I'll give you, let's say, 2.5 minutes to try to start this question and work it out. It's okay if you don't finish in that amount of time. But feel free to ask questions if you need some help. It's in the chat. I'll be staring at the chat. All right, give you about 40 more seconds. Again, it's okay if you don't finish it up because you'll have time while I'm working this out anyway to keep working. Okay, so yeah, we want to repeat the previous example. We're going to go through the same steps basically. It's just going to be a little bit harder to find the determinant of a minus lambda I. So the matrix A minus lambda I is basically you're just going to take A and just subtract lambda from the entries down the main diagonal. And now we want to compute the determinant of this matrix. And the way we do this is we might as well use the cofactor expansion along the third row, right? Because most of the entries in our third row, are 0. Okay, so to do the cofactor expansion, it'd be 3 minus lambda times the determinant of the 2 by 2 matrix you get when you remove the third row in this third column. Okay, and then once we solve this determinant, and I'm asking you this now because there's a delay, what do we do once we actually write out the expansion? Yeah, Taylor, exactly. So once we multiply all this out, we get this term, which factors into lambda minus 10 times lambda minus 5. We set it equal to 0. And we see that 3, 10, and 5 are our eigenvalues. And each has multiplicity 1. Okay, but you could imagine if we didn't have this row of and this column of almost all zeros, it would be pretty hard to compute this determinant. So eventually we'll come up with some better techniques to find these eigenvalues. But for now, this is a good way to find them. So are there any questions? Okay, if not, we'll move on to 5.3. Before we do that, I'm going to post some practice problems onto Canvas tonight to review for the test, which is next weekend. Okay, so if you go onto Canvas later tonight and there aren't any practice problems, send me an email and remind me that I promised you. And you have video evidence. You literally have video evidence of me saying this. So there's no way I could get around this. Okay. So let's move on to 5.3. Which is diagonalization. basically what we're going to do is we're going to express our matrix as some matrix times a diagonal matrix, which means the entries are only on the main diagonal, everything else is 0, and times some other matrix. Doesn't really make sense in words, but when we write it out, hopefully it's clear. So in many cases, the eigenvalue eigenvector information contained within a matrix A can be displayed in a useful factorization. Of the form A equals P inverse D P. Okay, so we're going to take our matrix A and write it as this product, P inverse D P. Each of these are matrices. We don't know what they are yet, but D will be a diagonal matrix, meaning the only entries of D, the only non-zero entries, are on the main diagonal. And this factorization, we'll see with some examples, will allow us to compute the multiplication A raised to a really high power really easily. So this is useful for computer programming. Okay, because you could imagine, let's say we're looking at, let's say multiplying by A with some sort of nice linear transformation that rotates or shifts or stretches our like some sort of picture, like what a phone would use. Remember, you could multiply by a matrix, and maybe sometimes it rotates the picture. And let's say you want to rotate it a bunch of times, so we'd have to compute this A to the K matrix. And this factorization is going to allow us to do it. And so we'll come up with some techniques. It'd be really easy to tell a computer how to do this. Okay, but first, let's just take a look at what happens when we raise a diagonal matrix to a high power. Okay, so we have this diagonal matrix, 5, 0, 0, 3. And the question is, compute D squared. So D times D. Compute D to the third. which is d times d times d, and then find a general pattern. So what is d raised to the kth power? So is there a fast way to compute d to the 100th, for instance? Okay, so I'll give you a minute or so to work this out. Please type in any questions or thoughts that you have in the live chat. Okay. Well, let's first start by computing d squared. And then that'll help us compute d to the third. So d squared is equal to d times d. So this first multiplication would be 25 plus 0, 0 plus 0, 0 plus 0, 0 plus 9. Okay, so d squared is the matrix 25, 0, 0, 9. Okay, I'm going to work out d to the third now. And while I do that, does anybody want to share what they got for d to the k? So d to the third is d squared times d. And when we work this multiplication out, we get 125, 0, 0, and then the last entry is 27. And in general, d to the k is equal to, well, we're not going to go through and prove this by induction, but you could. D to the first has the entries 5 to the first, 0, 0, 3 to the first. D squared has the entries 5 squared, 0, 0, 3 squared. D to the third has 5 to the third, 0, 0, 3 to the third. And in general, d to the k is the matrix 5 to the k, 0, 0, 3 to the k. Okay, and so this fact that it's really easy to raise diagonal matrices to high powers is going to come in handy. So let's look at another example. So Let A equal the matrix 7, -4, 2, 1. So note that A equals P D P inverse, where P equals 1 minus 1, 1, 2, and D is equal to 5, 0, 0, 3. Find A to the K. Okay, and we're not going to work out this whole question now because it's going to take us a few minutes. But I'll tell you what steps you should do. And you could try this weekend and we could talk about it on Tuesday. But first things we should do is find P inverse. So find the inverse of this 2 by 2 matrix. And then just observe that A to the K is equal to, well, it would look like P D P inverse times P D P inverse times P D P inverse. Right, K times. And so A to the K equals, well, these, every time you have a P inverse times a P, that is the identity matrix. So we don't need to include these. Okay, so what's left over, there's a P on the left-hand side. There's going to be K copies of the matrix D. And then there's a P inverse on the right-hand side. Okay, and so this should be pretty straightforward to compute. So this is how we'll start class on Tuesday. Okay, but that's all I have. That's all I have for now. So I'll stay around for a few minutes to answer questions. If you're in the 9 o'clock class, your quiz will be available in 3 minutes on Canvas. Make sure when you open it that it is not a calculus quiz, because that is what happened to the 8 o'clock class. But yeah. So yeah, I think it was a successful first week of this online world we're in. Let me know if you have any questions. I'll be hanging around here for another couple of minutes just answering questions. Of course, make sure to hit the like button on your way out. It'll help us get to 1,000 subscribers, which is going to be awesome. Thanks, Taylor. Have a good weekend as well. Everybody, be safe, be patient. Just let's follow the rules and, keep our distance from everyone. We'll get over this in hopefully a few weeks. I don't know. I'm not an inspirational speaker. But yeah, have a good weekend, everybody. All right, if there aren't any more questions, I'm going to end the stream. Bye-bye.